Nice to see everybody. Sorry, the class before us was running late, and I flew in at 1 o'clock in the morning from Washington, D.C. So it's been a heavy 24 hours. So nice to see you all. Let's see. I guess the main thing that you're all concerned about in the coming couple days is your midterm. So friendly reminder: you have a midterm on Wednesday. If that's coming as a surprise to you, something has gone severely, severely wrong. A few reminders I'll keep giving. The midterm includes all content up to and including the last minute of today's lecture. Let's see here. It begins precisely at 11:05 a.m. on Wednesday, and it will end precisely at 12:25 p.m. rather, on Wednesday. If you guys show up late, you don't get to start late, you just lose that time on your midterm. Hopefully all of you who have accommodations have now heard from our staff with plans. If not, do let me know, either at the end of lecture or by email. We'll make sure that happens. You are allowed 1 page of notes. It is to be handwritten and on a single sheet of paper. No, you cannot design that page of notes on your iPad and print it out. I want you to suffer. I want you to write it out because I want at least one time in your life for you people to write down the equations that are relevant in this course and not use some weird digital tool to do it. So, sorry, I'm a grumpy old man, and that's the way it is. Obviously, you have an accommodation about handwriting stuff that's different, and you can let us know. I believe those are all and there's a practice exam on the course website. If you're looking for more practice materials, you might notice that this course, unlike many courses here, like I literally made every piece of material for this course, like the textbook, the slides, everything. What that means is you've probably figured out my aesthetic by now for like the kinds of questions that we tend to ask on exams and homeworks and things. So you can more or less invent your own exam pretty easily. Go through the ends of the book chapters. Both for the practice exam and for the book chapter things, you're more than welcome to discuss with each other. Post questions on Piazza, come to office hours, do them together, whatever. It's completely fine. There's no cheating concern there. No, the practice exam does not have written out solutions, but like if you guys work together and make some, great, share it with each other. That's fine. Right. So, any questions, comments, concerns? Cool. I should warn you guys, like the practice exam, I think was on the difficult side. This one, Leticia and I are negotiating the difficulty level. Of course, the final grades in this course will be adjusted to account for the difficulty of the exam. It's really hard to write a well-calibrated exam. So, I get to make you suffer a little bit for an hour and a half once a semester, twice a semester. And that's my prerogative, to quote Britney Spears. Okay, so with that, today we're going to continue our discussion of optimization. We're a little bit behind the course calendar, but that's fine, despite my discomfort with, uncertainty. So today we're going to continue talking about minimizing functions. That'll probably go into, I would guess, the next 3 lectures or so. And then we're going to get even more funky and talk about very special cases of optimization. In particular, we're going to talk yet again about linear solvers, but from the perspective of the tools we've developed for the last couple lectures. Okay? So for now, for today's lecture, and probably for at least part of the next one, our goal is going to be to optimize functions f of x subject to no constraint on x. And for the most part, we're going to assume that f is differentiable as many times as we wish, although the very first algorithm we cover today is only going to need continuity, which is kind of cool. So we talked a little bit last time about the terminology of optimization. In particular, we talk about minimizing a function a lot, but of course, a picture that probably I hope you've all drawn in like college calculus class is the fact that the word minimum is a little bit suspect, right? Because oftentimes the thing that our algorithm is able to find is a local minimum, but the thing that our brain wants it to find is a global minimum, right? So like a function like this point, from the perspective of like wiggling around a little bit in a neighborhood of that point, looks like a minimum, but of course if I went far enough away, I could find a lower value of f. I think that schematic is a pretty familiar one to the students in the class. And so I think most of our algorithms are going to live in that second category. And we're also going to talk a little bit about just double checking, like when your algorithm converged, can you make some, for example, Taylor series style argument or use some property of f to verify that you actually reached a local minimum, right? In other words, if your algorithm converged, are you happy with the result? And actually what we'll find is that that's a little bit more of a subtle picture than you might think. So for example, like just to get your brains thinking about this a bit, let's say that I'm running an optimization algorithm, and so it's giving me a whole sequence of points x, and maybe f of x decreases in every step, and the values of f of x converge. Does that mean that my algorithm actually found a local min? So that sentence was a little bit poorly phrased. Let me try again. So I make a sequence of points x in my algorithm, right? Like gradient descent, whatever. And I evaluate f at every single point. I evaluate my objective function, and I see that it's decreasing and eventually kind of stalls out. Like the amount of decrease goes to 0. If I report that number, is that enough to say that my algorithm actually reached a local minimum even? No. Why?
Because you could have found a maximum.
You might have found a maximum. So for Newton's method, that's absolutely right. Any other concerns? Yeah. There might not exist a minimum. Anything else? So anybody remember like Zeno's paradox? How this one goes? So this is the one where like it's like some kind of tortoise and hare situation. I forget the story behind it, but for some reason like the tortoise or the hare, I don't know, the mythical creature of some sort is in a race and it does a stupid thing, which is it takes a full step, and then half a step, and then a quarter of a step, and then an eighth of a step, and then I don't know, I can't do math beyond that. And so like, what's the total distance that you travel? 2, right? And so you're in that case, like for example, you can imagine your optimization algorithm, like your x's actually converging to some number, like during gradient descent. But it could easily be that it just stalled out. You just were so conservative with your step size that you never actually reached a minimum or anything else. You just kind of gave up, right? Or it could be you measure the value of f, and the values of f converge, but you actually didn't reach a minimum. So for example, like On pointed out, maybe I have some function like this, and so the values of f of x converge, but the x's go off to infinity. So these are the kinds of cases we have to worry about in optimization. It's actually quite subtle. So there's a lot of different ways to do that. We'll talk about one, which is just a posteriori. Your algorithm thinks it converged. Maybe we check the gradient of your function, make sure it's close to 0. And then like, I think we suggested over here, we need to make sure we're not a local maximum. So we might look at the Hessian, something like that. Or we work in a particular class of functions that we can say more about. So for example, if our functions are bowl-shaped or convex, which happens a lot in the computer science world, then we know if we found a local optimum that we're actually at a global optimum, right? So those are like 2 different things we could do. Let's talk a little bit more. Okay. So at the end of our last lecture, I began to justify an algorithm which is the most famous optimization algorithm, especially in 2025. She's a big hit among the machine learning community. And that algorithm is gradient descent. And inside of gradient descent, I think like all of you guys, every morning you're brushing your teeth, you're saying your morning rituals. You turn around 3 times, speaky smells, whatever, and you repeat all your favorite phrases to yourself. And in particular, one of those phrases that comes up is that the gradient direction is the direction of steepest descent of my function, and that's why gradient descent converges. Here's the first question you should ask when somebody says that is like, why the heck is the gradient the right thing? Right? Why does the gradient point uphill or downhill? I mean, if you think about it, like, what is the gradient of a function? Well, I mean, I think most of us would say, okay, the gradient of f, usually defined, at least in college calculus textbooks, to be this weird vector of just partial derivatives, right? And obviously this expression looks a lot like a bunch of coordinates. Why does this have anything to do with walking uphill or downhill? Anybody have any suggestions? The fact that nobody's raising their hand is actually quite concerning to me, because this is the thesis of machine learning. Yes, Madeline. Yeah, so Madeline's got like a clue as to the right thing. It's like we're in some local neighborhood. We're trying to quantify how much it changes. And how could we kind of formalize our approach to that? Yeah, Hamid.
We think about like directions,
Mm-hmm.
and we define this notion of like directional derivative, basically a dot product of the vector.
Yeah, so there's like a dot product of the vector and the gradient. In particular, I think there's one expression that helps enlighten us a little bit, which is the following. Let's say that I'm at x, and I move a little bit in some direction d, or delta maybe. Sorry, I'm glancing at my notes because I prefer to have the same notation, which I've already failed at in like 2 seconds or less. That's okay. Okay, so to first order, what is this thing? Well, we've got an f of x plus, and now this coordinate-wise expression, the kind of nice thing is you can kind of repeat Taylor's theorem in one coordinate at a time, which is something you hopefully did in calculus class. What you'll find is that this is equal to f of x plus the dot product between delta and the gradient f of x plus some fudge factor that scales quadratically in delta, right? In fact, we already used this expression a bunch in this class. So I think this is absolutely true, right? And notice, like, as delta gets small, which is the regime that we care about in gradient descent, this is the term that dominates, yeah? So now, again, what am I trying to justify? I'm trying to justify that delta is the direction of steepest ascent. You have to be careful, gradient descent goes down minus delta. Does this thing give us any clue, at least locally in a little small neighborhood? Yeah.
If you take delta to be like a very small vector of consistent, like I don't want to say unit vector because that's not small, but
Yeah.
Then the dot product is maximized when it's in the same direction.
Yeah, so let's see if we can formalize that intuition. So let's do two things. First of all, let's say at the very least, I would like this number to be less than that one. Yeah? Like that seems like, I mean, that's not the same as steepest descent, but at the very least it's descent. By the way, a phrase that shows up a lot in optimization world is descent direction, which is basically exactly this. In other words, we would like this term to be less than or equal to 0, right? Otherwise, delta is a pretty terrible direction for optimization, yeah? So one way that I could do that, notice, is if I take delta to equal any positive constant times grad f, right? Or sorry, any negative constant. Actually, I'm going to keep confusing ascent and descent today. Then what's going to happen? Well, in that particular case, when we get f of x plus, I put a minus in front of it, minus c grad f at x plus big of I guess basically c squared. Yeah. So in this particular case, what do we know? Well, for small enough c, I think in my textbook I used t, my bad. This number is negative, right? And it's basically just using the fact that norms are positive numbers, right? So at the very least, we've convinced ourselves that stepping a little bit in minus the gradient direction decreases our function. That's a good thing. And in fact, to kind of formalize some intuition we had before, we can use a very particular inequality, which is one of our favorite ones. It's called Cauchy-Schwarz, right? Which says that the dot product between two things is upper bounded by the product of their norms, like that. Yeah. So, okay, so to first order, I'm going to use kind of fudgy notation here. I'm going to throw out that last term. Yeah. What do I get? Well, for now, let's say that I want to increase my function. The decrease argument is the same, but I'm going to stick a bunch of minuses and get myself confused. So, well, this thing is upper bounded, or the norm of gradient of f x squared plus whatever, right? And the Cauchy-Schwarz inequality has an equality when a and b are parallel to one another. Yeah. So notice this is actually what's going on when we talk about the gradient being the direction of steepest ascent of our function. Is because the first order term in our Taylor series is this dot product between the search direction and grad f, and the dot product is maximized when those two things are parallel. Yeah, and it's minimized, by the way, when they're anti-parallel, when they're minus each other. Okay. So anyway, this is all just to say that, like, what I want you guys to start doing is interrogating these algorithms that you know and love. You know, like the very first thing you learn in machine learning class, or I suppose operations research class, if that's your bag, is gradient descent. And we all, you know, like, we all have like a t-shirt that says the gradient is the direction of steepest ascent. But actually that's not like a given, right? If this is your definition of gradient, it's not entirely obvious that should be the case. And so these are the kinds of things we have to check. So in particular, notice that there's one case here, which is the one that we usually are hoping to find, which is the point where grad f equals 0, in which case this term vanishes. And then we usually call this thing, you have to be careful, it's not a local optimum necessarily. The correct term here is stationary point, right? So for example, oh, that's fun.
Sorry about that.
That's okay, it's not your job. If my function has a stationary point, I might have a function I'm optimizing like here, where it's flat, but neither is a local optimum or maximum or minimum, right? So this is just like, to first order, it's stuff. Right, so like last time I suggested that essentially optimization and root finding are closely related to each other, right? Because we could talk about min over x of f of x, at least in the differentiable case, as being somehow related to finding an x where grad f is equal to 0. But notice that our job isn't done, right? Because points like this guy or these other two all satisfy this condition, but not all of them are even local minima. And so essentially a very typical kind of loop in optimization algorithms look like the following. So you might find a critical point, like any one of these three things, and then if you're trying to not be morally reprehensible, after you find that point, you should check that you actually succeeded in solving the problem you wanted. Yeah. In other words, that you want to check that it's at least a local minimum, right? And we'll talk about a few different conditions that you can check for this kind of thing. What we'll see is certain algorithms, like Newton's method, can actually converge, for example, to a local maximum by accident. Other algorithms, like gradient descent, probably won't reach a local maximum, but they still can actually reach a saddle point and get stuck. And so these kinds of things are important to do in reality. And then, of course, step 3 is, I would argue, one of two things, like either repeat, so like, for instance, if you didn't find a local minimum, you could start over from a different starting point or perturb a little bit and keep going. Or I think what's popular in modern optimization software is to just kind of vomit in that case, like, oh, oops, I converged, but I didn't find a good point. No, too bad. I think is what a lot of these tools do in reality. But at the very least, it's better to know that information than to think that your optimization tool did something that it didn't. Okay, so one other object that we're going to need in our lectures on optimization, we talked a lot about gradients, and that's enough to do gradient descent, of course. The second thing that we might need is a Hessian. And in this particular case, now we can take our Taylor series and we can expand it to two terms. So remember that the Hessian of f is its matrix of partial derivatives, of second partial derivatives rather. Do we know any good properties of the Hessian? I'm moving fast because I'm hoping this is review of calculus class. Yes?
It's symmetric.
It's symmetric, right? Because partial derivatives commute. If I differentiate a function in x and then y, that is the same as differentiating in y and then x. By the way, if anybody can manage to draw like a fun schematic that actually illustrates that fact, it's like shockingly difficult to do that, at least for me. Like it's a thing that's easy to derive algebraically, but I've always kind of struggled to draw a picture of it. There's like a slightly souped up version of this that's really important differential geometry, and I've never managed to get it right. But in any event, this is symmetric matrix, and we can expand f to look to second order like the form on the board. Yeah? Notice immediately this suggests an algorithm for optimizing f by borrowing from our lectures on root finding, right? I could find, well, like, what is the minimum of this function? Well, I take the gradient and set it equal to 0, yeah? So essentially what I'm going to find in this case is that x is equal to h inverse times the gradient of x naught, yeah? And notice this is exactly Newton's method applied to this problem, this root finding problem. Yeah? This might be a formula you put on your exam study sheet. You don't want to remember this. Okay, so in any event, beyond suggesting an optimization technique, this also suggests a way to check if we are actually at a local minimum or not, right? By the way, if this formula is confusing to you, think of the one-dimensional case where h is just like a number, right? And this whole thing is just like a parabola, yeah? So for example, if we're in the 1D case and h is negative, what does that mean? Well, that means that my function bowls down, right? And then if my gradient were 0, so that second term isn't there, have I reached a local minimum or a local maximum? It points down. A local maximum, right? That's not so good. Notice that Newton's method doesn't distinguish between the two. Oh, oops, by the way, this is x is 0 minus this thing. I'm so sorry. I'm surprised nobody caught that. Okay. Right, so I think there's this little table that we all learn in calculus class, I hope. If not, then no time like the present. Which says the following. Essentially, let's say that I found a critical point of my function f. So now grad f is equal to 0, right? So now the dominant term in my Taylor series, if I want to know what it looks like as I wiggle around x0, is this third guy, right? And what do I want? I want it to bowl up, because then I'm confident that at least in some neighborhood of x0, I've reached a local minimum, right? So in that particular case, that corresponds to H being a positive definite matrix. And in fact, if you're not confident in that fact, I think you can all apply the definition of positive definiteness to kind of verify that. Do you see that? Because if H is positive definite, notice that that third term in the Taylor series, if x is not equal to x naught, is going to be positive, yeah? Which means that as I move x away from x naught, it increases, and hence x naught is a local minimum. It's easy to get the sign of this thing upside down. There's a second case where it's negative definite, and then you're at a local max. A third one, where some eigenvalues are positive, some eigenvalues are negative, then you're in that saddle point case. And a fourth really irritating one, which is that HF isn't invertible. In other words, it has a 0 eigenvalue. What can I say in that case?
Get some sort of like weird like flat oddity or something. And are we like semi-definite?
So we get some weird flat oddity. Yeah, that's true. So to like quote the 2024 political campaign, it's certainly weird. Can I say it's a local max, minimum, anything? No, it's indefinite, right? So in particular, if you're looking, remember that I keep encouraging you guys to think of like the simplest examples every time you think of these functions. Let's think about f of x equals x to the fourth. Hopefully we all agree this function kind of looks like that. Yeah? Notice that x equals 0 is a local minimum, but f double prime of 0 is just 0, so it actually doesn't tell us anything about the function nearby. I think this is like relatively uncommon in optimization. However, it actually does come up. So for example, one very common thing that people do is if you want to enforce a constraint in your optimization problem, like g of x equals 0, maybe I take g of x and I just like square it, and then like put a giant coefficient in front of it. And that action of squaring often will cause this kind of thing to show up locally. And what we're going to find is that makes your optimization problem very ill-conditioned. Right? Because like in some local neighborhood, you see that like backward error and forward error are pretty decorrelated with one another. And that's going to be a problem. Okay, so this is the sort of like high school calculus version of figuring out whether I'm at an optimal point, right? My optimization algorithm converged. I found a point where grad f is pretty close to 0. I check the Hessian. If I'm really lucky, it's positive definite. I say like, ta-da, I've got a local min. That's great. But that's actually not the only way that we can check whether we have a local minimum. There are many others. And they require oftentimes a little bit more structure on your function f, right? So currently our function f is just differentiable. Notice if it's not even differentiable, then like none of these things apply, and we've got to think through what that looks like. A different thing, which is very common in fancy college level optimization techniques, is to say, well, I know a little bit more about f. Namely, I know, for example, that f satisfies a certain inequality, which is articulated on the board. And this inequality is known as convexity. So the idea of convexity, draw a picture on the board here, is that I have a function, and basically, like when I hear the word convex, you should think bowl-shaped. That's the sort of word to think about here. And the idea of a convex function, so there's our minimum. If I take any other 2 points, like x and y here, and evaluate my function of these things, I could linearly interpolate between the values at those 2 points. Right? Notice that is the right-hand side of our inequality. Right? So it's a linear interpolation between f of x and f of y. And then essentially, the property of convexity says that f sits underneath that graph. And if you think about it, so let's draw a picture where that's violated. So for example, let's say that f goes down for a bit, goes up, and then goes down again. Let's see if I can manage to choose 2 points that make this fail. So let's say I'm at this guy and that one, right? Now I draw that straight line. I learned from Eric Domain that you look at the point that you're trying to draw the straight line to. Looks like it worked okay. Notice in this region, f went back over that line, so this would not be convex. And notice this function has 2 optima locally. So f is a complex function when it satisfies this property. It is, I always forget, is it strictly or strongly convex when the inequality is strict whenever x is not equal to y. But in any event, what convexity tells you is that you can't have a local optimum. In fact, the textbook justifies this very carefully, right? The proof is very straightforward. Basically, what you would do is say, oh, well, if I had a local optimum and then some other point with an even lower objective value, then essentially on this line in between, somewhere it has to go up, right? Otherwise, you kind of contradicted the definition of local optimum. Okay? And so actually a very modern approach to differential optimality is not to check the Hessian condition, but rather to just say, convince yourself before you even start the optimization procedure that your objective function is convex. And then you know, for example, if Newton's method converged, right, it reached a point where graph is 0, there exists no local maxima, so you're kind of okay. Right, so this is a different way to convince yourself that you're locally or globally optimal in this case. If you like this kind of thing, there's a beautiful area of optimization. It's so cool. We're not going to have time to cover too much in this class, called disciplined convex optimization. I like it because all of you people could use a little discipline in your convex optimization. But the basic idea is it's actually a link between convex optimization and programming languages, which is super cool. And the idea is that there's a bunch of composition rules for convex functions. So for example, if I add 2 convex functions together, the result is also a convex function. If I scale by a positive constant, then that thing is a convex function. If I shear it with a particular linear map, often that can be convex, so like f of ax for a certain kind of a. And so people have actually implemented programming language tools where you code up the form of f, and then it kind of applies those rules formally to check to make sure that your function is convex. And it just refuses to optimize it if it's not. So a very typical tool for that is something called CVX, which is like totally, for example, revolutionized the way that I do research, because essentially it separates out the modeling part of your problem from the optimization part. So like if you use CVX, it will force you to think in this universe. And then in fact, it's even better than that because it knows how to like look in its library of optimization algorithms and figure out the one that's relevant to your particular objective. The trade-off for that is it's very slow. So, you know, what are you gonna do? Right, so one reasonable question that students often ask, although you people are quiet this morning, is convexity the only condition that guarantees that local optima are global? Does anybody have an idea? Yeah.
I think no.
You think no? Yeah, tell me more.
Something that maybe that is not necessarily the case, but like we sort of like branch off in a less than convex way, but it's always running downhill.
Yeah, so always running downhill is like a pretty good intuition. There's in fact a lot of different function classes that have these kinds of properties. A very typical one is something called quasi-convexity. So here's an example on the screen of what quasi-convex functions look like. Notice this guy is not convex. I've drawn you a point here where it sits above the linearization. Essentially what quasi-convexity does is it replaces the linearization with a weaker condition, which is that you're less than or equal to the max at the 2 endpoints. If you evaluate here and here, you take the bigger value and then you draw like a horizontal line. Quasi-convexity is sufficient. Notice that convexity, if you are convex, you are also quasi-convex. The reason this is less popular in practice is that composition rules for quasi-convexity are not so nice. So like if you go back through and you like check like, can I add them together? Can I add them as constraints? That kind of thing. You'll see pretty quickly that that's not the case. So for example, let's say I took this function and I shifted it to the right. Right, so now I've got one guy with a dip over here, another one that has dip over here, and I add those things together, then I get a function with 2 dips. And so like essentially this is a property that is sufficient if you get so lucky, but it doesn't come up so often in practice. Cool?
Is the intuitive idea of quasi-convexity that the function might like rise above that interpolated line, but not apply it too much.
That's exactly right. Yeah. So, by the way, just to dispel one additional myth out there in the computer science world, oftentimes I think we all think of convex problems as easy. And in some cases, that's actually true. Like, if I manage to find a local optimum of a convex problem, then at least I'm convinced that there's not some other solution out there that's like even better. Can anybody, but like what I haven't shown is that there exists an algorithm, some like universal algorithm for convex optimization that takes a convex function and then outputs its minimum. Right? Like for example, one could imagine a universe where you say, oh, like if convex functions are so nice, gradient descent is good enough and like it'll always converge in some reasonable amount of time. That could be a conjecture, and in some sense it's verified experimentally, because the typical cases that we do computationally, convexity is a very nice property to have. But unfortunately, it turns out that convexity does not imply easiness necessarily. And there's some really crazy convex sets out there. Just to give you an example. By the way, if you guys haven't noticed, this is like my research field is optimization, so I get really into this stuff. I can give you counterexamples for days. So, quick exam review. Let's say that I have a set of semi-definite matrices. What is that set? Let's think about it. So it's the set of matrices A, maybe in R n by n, with the property that X transpose A X is greater than or equal to 0 for all X in Rn. Right? Hopefully we all agree that this is a set of semi-definite matrices. Fun fact, these matrices admit Cholesky factorization. Yeah. Mm-hmm.
You said semi-definite, but positive semi-definite?
Positive semi-definite. Yeah, that's the shorthand. I think it's pretty rare for negative semi-definite. Good question. Here's a fun thing that I can do to this definition. Let me define for you a slightly larger set of matrices. I have to be careful, like larger and smaller, but let me define for you a superset of semi-definite matrices, which is the following. So I'm going to look at the set of matrices A and R n by n. Oh, by the way, sorry, I'll pause for a second. Can anybody give me an algorithm? In fact, let's say that we're for checking that a matrix is positive definite. Just as some exam review. Yeah.
I'm gonna try to Cholesky factor.
That's right. You can try to compute its Cholesky factorization, and if it succeeds, then it's positive definite. And if it doesn't, then it didn't, right? Because we actually showed in class that our algorithm always succeeds for positive definite stuff. So now let me give you a slightly different set of matrices. Is the following. For all X, which is in Rn, but I'm going to add one condition, plus. So this is a weird set of matrices. What it says is I want the set of positive, like I want this inner product to be positive, but only for x's whose entries are positive. Now for one thing, you guys see that this is a superset of this matrix, this set of matrices? Right, because if you are semi-definite, then in particular for any positive x, you have this property. But there are matrices A that satisfy the second condition and don't satisfy the first. If you're curious, it's called copositive. And this is a convex set of matrices. For example, you can convince yourself pretty easily, like if A and B satisfy this property, then A plus B also satisfies this property. Yeah. Can anybody come up with an algorithm for checking if you're in this set? Think carefully. Oh, that's too bad, because if you did, you could make $1 million, right? This is so this is an NP-hard problem to check if you are even in this convex set. So in fact, this is just like to dispel a computational myth that's out there. That convexity does not imply easiness of solving problems. But there exists big classes of convex problems that are easy to solve. In fact, you can define all kinds of wild convex sets. So for example, you could look at the set of C++ programs that take exactly n bits, and look at just the set of C++ programs of n bits that terminate, right? And look at the convex whole of that set, right? So that's a really weird object in some very high dimensional space, and its corners are programs that terminate. Right? So it turns out that like you can kind of take problems like the halting problem in computer science and reduce it to convex optimization, which is pretty weird. Yes?
So we were talking about convex functions. Is there like a specific definition for a convex set that we're talking about?
Oh, I'm sorry. Yeah. So that's a good question. We talk about convex function. This is a convex set. One way to define a convex set is a set whose indicator function is convex. So if I define a function that is infinity when I'm not in the set and 0 when it is, right? Then that thing is convex exactly when this set is convex. Usually I think the definition goes the other way, but that's fine. Good question. Yeah. So this is all to say, I just wanted to dispel a quick myth because it comes up a lot in our graduate students. Convexity is an important and useful property, and it allows you to do things like a posteriori, I find a local minimum and I could be convinced that there's nothing better. On the other hand, it does not imply easiness of computation. There are a lot of easy convex problems out there in the universe, but that's certainly not all of them. And so if you go out there and take a convex optimization class, which all adults in 2025 should, you'll learn many classes of convex problems that are easy to solve. But that's very different than the full set. Okay. I heard like a noise. Yes.
Does that mean that you can't reduce the problem of like solving for the membership in one convex set to another convex set? Like there.
Oh yeah, no, absolutely. There's some convex membership problems that are a lot easier than
And some of them reduce to NP problems.
Yep. Yeah, which is a weird thing. We don't usually think about the intersectionality. Cool. Okay, so now let's actually put all this theoretical stuff aside and talk about algorithms. Notice I'm stalling a bit because I know your midterm is on Wednesday and I don't really want to prove convergence of gradient descent today. We're going to get halfway through that and then I'm going to start rushing and that seems like a bad outcome. Okay, so, right. Already we've kind of talked, so for now, let's talk about optimization just in one variable. So in particular, remember we have an algorithm already for finding roots of functions. And in particular, Newton's method could be applied to the problem on the right? Like if we think that finding optima of f is the same as finding roots of f prime, that immediately suggests an optimization algorithm that's suggested on the board. Notice that this version of Newton's method is one derivative higher than the version we saw for root finding, which hopefully makes sense. By the way, you have to be a little bit careful when you go out there in your numerical analysis careers, when people use the phrase Newton's method, I think typically they're referring to the optimization version, but the reality is it's a root finding algorithm that is applied a lot to optimization. And notice that this already inherits a lot of the nice properties that we have, for example, second order convergence, at least when you're close to an optimum. We already wrote a formula, God no, for how to do this in higher dimension, but you just take this formula and lift it exactly the way you'd expect. So it's like an inverse Hessian sitting in front of grad. Now, I think a reasonable question, given our discussion of root finding, it's pretty obvious how to lift Newton's method to higher to optimization problems. But you can say, well, wait a second, Justin, like you started our discussion of root finding by talking about bisection, and then eventually we got to secant method. What about those guys? Like, what can we do there? Notice that secant method applied to optimization in one variable is a little weird. It would get rid of the second derivative, but not the first, right? So like there's not too many settings in 1D where you would finally encounter that. There is a version of secant method that makes a little bit more sense to me, which is something called successive parabolic interpolation, which is pretty much exactly what it sounds like. So remember what secant method did is it took the last two steps of your root finding problem, it drew a line, and then used that to predict the next root. So in successive parabolic interpolation, anybody want to guess what that thing does? Yeah.
You draw a parabola tangent to the 2 points there.
Not quite tangent. You take the last three steps of your algorithm, fit a parabola to that, and then take its minimum to be your next iterate. This algorithm is relatively rare in practice. If I recall, the convergence is not so great. But we'll talk about one alternative, at least a bisection, that we can use in the optimization case. Okay? So in particular, here's kind of a fun thing we might do. Let's see that like we ask this question in one-dimensional optimization. Is there any universe in which we can imitate that bisection algorithm? Remember what bisection does for root finding? Quick exam review. So let's say that I have a function like that. I bracket a root, right? Then essentially, as long as my function is continuous and I have a positive and a negative value, I can kind of do binary search, right? Like I can cut my interval in half. I notice that these two still vary in sign, so I know that I can get rid of this interval and continue recursively. Hopefully that sounds familiar. And basically what bisection was built on was intermediate value theorem, right? It said that like for a continuous function, there's never a case where my function jumps values. If I see a value here, a value there, every value in between has to be achieved, right? Now, a reasonable question you might ask is like, okay, so now I want some kind of bisection looking algorithm for optimization in 1D. What is the right analog of the intermediate value theorem in that case? And I would say it's not entirely obvious, right? Because like there's not the same notion of like achieving every value in between when it comes to finding a minimum as opposed to finding a root. Okay? And so what we're going to do is we're going to cover in one dimension a kind of fun optimization algorithm. This is super fun, actually. I love this thing. Which is specifically for functions that satisfy the following property, which is called unimodularity. And a function is unimodular if there exists a point x star, so that when you're looking to the left of x star, your function is decreasing. When we look to the right of x star, it's increasing. So this is a weaker condition than convexity. See if I can draw a picture. So I've got some point x star. Notice this only works in one dimension, kind of similar to like bisection only works in one dimension. So now my function can do all kinds of crazy things. It can actually have a discontinuity. that's perfectly fine. It can have like a non-differentiable point, whatever. So long as I have the property that if I have two successive points to the left of x star, the value on the right is smaller, less than or equal to the value to the left of it, right? And now I go back up, right? So convex functions are an example of unimodular function. Which is a good thing, because otherwise it's quite hard to check this condition in practice. But convexity is an example of like a sufficient way to do that. Yes, I see you.
There's no way at all to do this in more dimensions or equivalently.
No, right? Because like this is depending very much on like drawing a straight line, and like essentially in multiple dimensions, there's like a whole circle worth of points around your optimum you have to account for. Yeah. So there might be some condition, but it'd be pretty rare. Okay, so here's a cool thing about unimodular functions. Let's say that I have a unimodular function. I really want to say totally unimodular, but that's a pretty different order of math. Right, so other totally unimodular matrices are very close to my heart. Okay, so let's say that I have a unimodular function. Here it is. Maybe it has a discontinuity, a little kink in it, like that. The pictures are going to become really hard for me to draw because like I really want things to be symmetric about their minimum. And then this algorithm is going to work a little too well. Okay. So here's our x star. Hopefully we all agree. And let's say that kind of similarly to the bisection algorithm, we're able to bracket a root, right? So I have, or a minimum in this case. So I have a minimum between here and here. Sound good? Okay, so. Okay. Now, what do we do in bisection? Well, we just like chose the midpoint, evaluated our function, and then we tried to convince ourselves that like to the left or the right of the midpoint, we could just discard the whole integral. In this case, it's not obvious you can do that, right? Like it's not clear, like if I just like evaluate this function in the middle and I tell you the value is this, can you guys double check, like, can I like discard and say, oh, I know the minimum can't be to the left of that point? From the unimodular principle, it's not obvious you can do that. Let's think about it for a second. In some sense, the onus is on you guys to show me that you could, right? Like the intermediate value theorem says it crosses zero here, but it doesn't say there's a minimum. Yeah. So here's what happens in a really clever algorithm called golden section search. I struggle with the name of it. You say, okay, so 1 point isn't enough. Let's say I evaluate f at 2 points. Okay, so in particular, let me see if I can choose points that make this obvious. Maybe this guy and this guy. Okay, and let's call these points, if I peek at my next slide, so we're going to call, yeah, We're gonna call this A, this x0, this guy x1, and this point B. Okay. And here's what I'm gonna do. I'm gonna draw a horizontal line from the value at x1 across my entire function. The second horizontal line from the value at x0 across my function. Right? And now, here are the intervals I'm going to look at. This guy and this guy. So the interval from a to x0 and the interval from x1 to b. Remember, the only thing that I know about my function is that somewhere between a and b, it swaps from decreasing to increasing. That's it. That's all I know. Now notice, the value at x0 is bigger than the value at x1. Yeah? So what does that mean? That means, okay, so if I look from x0 to x1, at least kind of differentially near x0, can my function be increasing? No, because like in aggregate, it's got to get down to x1, right? And the second that I start increasing, I can never decrease again. That's the definition of unimodularity. I see it. Let me finish my sentence. So again, remember, unimodular means decreases and then increases. You can never decrease, increase, and then decrease again, right? So if my function increased starting at x0, notice that would be a problem because I see that x1 has a smaller value. Yeah. So necessarily, in like some little interval over here, it's decreasing. Does that make sense? So, what does that tell me? Can x star be to the left of x0? Right? So if it's decreasing this way and I move in that direction, it's increasing. So I can conclude that x star cannot occur in this interval. Does that make sense? I see your hand back there. Let's how do I initialize? Well, you have to bracket a point here, which is not always so obvious. One way that you can do it is kind of sample points until you find one that goes down and back up. And then you can convince yourself that you found it. Yes?
So you pick x1 to be less than, or like f of x1 to be less than f of x0.
That's right.
How do you know that that's the case? Like you might have.
You don't?
Okay, so your argument like depends on f of x1 being less than f of x0, then maybe f of x1 is picked further to the right. So.
Well, let's think about that case. So the question was like, okay, but I got lucky. X1 was lower than x0. Let's see if we can do this in our head because I don't feel like drawing. Let's say that I took this picture and I just reflected it right to left. Notice that the shaded thing reflects with it. So in particular, we can conclude that one of two things has to happen. Great question. Either f of x1 is bigger than f of x0, or the other way around. And in each of those cases, we can discard one of the two intervals, either on the left or on the right. Isn't that kind of sneaky? So notice that this suggests some algorithm that's kind of like bisection. Maybe we call it trisection. What's that algorithm going to do? Well, in every iteration, I take my interval, which I'm saying like, okay, I don't know where my minimum is, but I know it's somewhere between here and here. I divide it into 3. I apply these rules. That tells me that I can like slice out one of the two outer intervals, and then I recurse, right? Notice it's very easy to see that this thing converges linearly. And that's a perfectly effective algorithm. So essentially, this is our sort of version 1.0 of our technique, which is iteratively we remove sort of a third of our interval each time. So we're doing a little worse than bisection, right? We only get a third, not half, but like, yeah, you know, what's the third among friends? Now the question is, can we do even better than that? And this is like a really sneaky observation. In particular, here's one kind of interesting observation. Notice, for obvious reasons, in bisection, every time we bisected, we had to evaluate f one time, right, at the midpoint. And now I have to evaluate f twice, right? So in fact, this algorithm pays 2 times, right? Once because there's like a third instead of a half. And actually, the time complexity of every step of this algorithm is 2 times the time complexity of bisection. That makes sense? Okay, so we're going to try and fix that issue. This is like the sneakiest algorithm. I love this technique. This is an algorithm called golden section search. It's named after the golden ratio, which we'll see in a minute. And essentially, this is an algorithm for optimizing unimodular function that only requires one tap of our function in every iteration. Okay? So let's see if we can do this. This is another algorithm that, by the way, I really struggle to draw pictures of, because it's one where you derive a condition that only works if you get a ratio exactly right, and I'm bad at, because I'm an asymmetric human, I'm very bad at drawing the golden ratio on the blackboard, but we're going to try to do it together. Okay. So, by the way, this algorithm doesn't require differentiability, which is cool. All right. So here's going to be our conceit for this technique. Is we're going to say, like, I mean, why did we divide things in thirds? Well, that felt like kind of nice and symmetric, but like we didn't really have to do that, right? If we went like 1/5 of the way from the left and 1/5 of the way from the right, then we could remove 1/5 of the interval. It would converge more slowly, but we could do it, right? So in fact, here's what golden section search is going to do. It's so sneaky. This is, did I mention I really love this algorithm? It's so cool. Okay, so here's our interval, like that. I drew it really big because then I somehow feel better about the bad diagram I'm about to draw. In general, so one thing I could do is mark 2 points. And for now, let's say that A and B are just 0 and 1. Okay? What we're going to see is this algorithm kind of scales. So for now, let's say that I've bracketed my x star somewhere between 0 and 1, and I'm trying to lop off one side of the interval. Generically, I could say I'm going to place one of my function evaluations at a location alpha, and another of my function evaluations at a location 1 minus alpha. Right? So when alpha is equal to 1/3, then I have my trisection algorithm. As alpha goes to 0, I'm like lopping off smaller pieces. As alpha goes to 1, I'm trying to chop off bigger pieces. Make sense? Okay. So let's say, just hypothetically, we're going to think through one case of this algorithm, that I run through the rules on the previous slide, and it tells me I can eliminate this part of my entry. Okay? And now I'm going to look at the next step of my algorithm. This is the part that I tend to get wrong, so everybody pay close attention and tell me the second your professor gets it wrong. Okay? So in particular now, this is kind of like iteration 1. Now, in iteration 2, I know that my x star is somewhere in this interval, like that. Okay? So now, the left end of the interval is 0, the right end of the interval is alpha. Cool?
1 minus alpha?
1 minus. Good. You passed this time. Okay, so that's right. So now we've got 2 additional points, x0 and x1, which are like somewhere in between these 2 guys. Okay. So here is going to be the tricky idea of golden section search. Remember that, like, what did I do in bisection? I bisected, and then either the left or the right of the next step of the algorithm was the midpoint of the previous step. Well, I could try to do the same thing, and notice, conveniently, that alpha is inside of this interval here. Okay? So let's draw this thing like that. Okay? So notice I actually have a piece of information about f somewhere inside of this interval from the left to the right in the next step, because always, I mean, notice if I cut off the left interval, then I have the 1 minus alpha there. There's always at least one data point that persists. So here's the sneaky, sneaky trick of golden section search. It asks the question, can I at least reuse that number? So in particular, let's say that alpha, see now alpha's on the left in this previous iteration. We made the interval smaller, so it's probably going to end up on the right in the next step, right? So now, let's say that I have x0 and x1, like that. Right, so now notice if I can manage to accomplish this kind of funny thing, then I can reuse one of my values and only have to evaluate one other time. Now the question is, how do I do that? Okay. So in particular, what is x1? Well, we know that x1 is equal to alpha, but let's think about it this way. Remember how we defined x1? It's like the 1 minus alpha fraction of the width of the interval, right? What's the width of this interval? Well, it's itself 1 minus alpha. So x1 is equal to 1 minus alpha squared. You see that? That sentence was a little bit goopy, so I want you to like think it through a second. the width of this entire interval is 1 minus alpha. And we defined these 2 points to be this fraction of the way along our line. So one of these 2 factors is the width of the interval. The other of the 2 factors is the fact that we've only gone 1 minus alpha fraction of the way. Cool? Yes.
Is x0 and x, you're saying x0 and x are equidistant to alpha and minus alpha?
That's right. Okay. Moreover, we also know, because we inherited it from the previous line, that this thing is equal to alpha. Cool? All right. So this is screaming out at us to just solve this little formula for alpha. Right? So we have alpha is equal to 1 minus alpha squared, which, when I do my negative b plus or minus the square root of b squared minus 4ac, hopefully we're all kind of cool with that. Yeah. What I'm going to get is that alpha is equal to 1/2 times 3. I guess plus or minus the square root of 5. One thing you can convince yourself in this particular case is that you should do the minus because we're on the right-hand side. Like that. Okay, so here's the kind of cool thing about golden section search. It has, by the way, 1 minus this thing, 1 minus alpha is tau, which I believe is the golden ratio. So if you're like into Da Vinci, then apparently that's spiritually important. Okay, so what is this algorithm saying? And it kind of makes sense because remember that golden ratio kind of has something to do with self-similarity, and that's exactly what we did here. Essentially what we said is if we want to reuse our previous iterate, we can do so long as the fraction that we move along this interval is not 1/3, but is this random made-up number. Right, so in implementations of golden section search, typically you have to hard code this number as a constant. And then that's the thing that you use as your fraction in every step. By the way, one thing that we didn't argue, but you can quite easily, is you should do the other case where you do the interval on the right, and what you'll see is you get the same set of fractions. Kind of makes sense. Okay, so that's golden section search. Essentially, here's a picture of what it looks like. Here's a fun fact, like when I drew this in the textbook, you have to actually do the math by hand, because if you don't, then like this picture doesn't work out. So here, we have this interval AB. I have placed x0 and x1. Notice that actually if you look at the golden ratio, what you'll find is it goes a little bit more than 1/3 of the way in. And so notice what happened. Here we had f of x1 is clearly larger than f of x0. So I can discard this interval on the right. And if I look on the left, now x0 became x1. And the new x0 is kind of multiplied by that same fraction. And if you see, notice that like the second line is like a scaled version of the first one, right? So that's the formula. Yep. So notice this algorithm is still linearly convergent, right? I haven't changed because I'm still able to lop off a constant fraction of my interval at every step. In fact, I think that fraction is slightly larger than 1/3. And I reduced the number of function evaluations by 1 in every step. Isn't that cool? This is such a cool technique. Yes.
How do you check if the function's unimodular if it's not convex?
How do you check the function's unimodular if it's not convex? We mostly don't. This is just like a function. Yeah, I think convexity is largely the most important thing. Or one thing that people will do, which is a little sloppy, is say like, if I'm close enough to a minimum, then probably locally I'm unimodular. So you can like try to run this algorithm, and if it succeeds, then a posteriori you could say like, haha, like I found a minimum. But you better be awfully careful doing that. Yeah.
If evaluating our function is cheap, are there cases where we prefer the 0?
I don't think so, actually. If I recall, this one still like actually lops off a larger fraction than 1/3. So you might as well use it. Yeah. Me.
I think like one thing that happens a lot in practice is that the norm function is like a sum of the decreasing and an increasing function.
Mm-hmm. Yeah, I think that's right. Like in statistics, or like there's a bias variance trade-off or whatever, you kind of know like if your parameter is too small, it's going down, and eventually it goes back up. We've seen plots like that a lot in this class, so it's actually pretty recently encountered this convention. Yeah, good point. Yes.
Just out of curiosity, are there algorithms that use like the mean value theorem?
The mean value theorem in multivariable cases. almost certainly there's a giant zoo of missing dragons out there, but like I don't know offhand. Yeah, that's a good question. Yeah, look it up. Let me know. Okay. Right. So that's our technique. Whatever. Sorry. There's our algorithm. It's a little bit ugly in pseudocode, but the picture is pretty easy. Okay. So anyway, I don't think there's any reason to spend like a whole month on one variable optimization. That's a pretty boring problem. So now what we're going to do is go to multiple variables. And obviously our goal probably for the next lecture is to justify the gradient descent algorithm, which is our first example of an optimization technique that works for multivariable problems when they're differentiable. The other one being Newton, which we already kind of mentioned. I think it's important to justify that algorithm in 2025 since it gets broadly used. In this class, we don't know what a random number is, so we'll do the deterministic version. But the stochastic one is basically the same proof. You just stick some expectations in the right place. Before we do that, in today's lecture, what we are going to do is talk about, at least when this problem is well posed, and some of the basic patterns that occur in multivariable optimization techniques. Because there's like some basic things that happen across many of these algorithms, and they're worth covering by themselves before diving into the particulars of these techniques, especially because they change all the time. I mean, it used to be gradient descent, then it was Nesterov and Adam and so on. Or in smaller scale problems, you can get second order convergence using Newton method. But before we talk about any of these, what we're going to do is introduce a little bit of terminology to see that like there's broad conditions you can check on a generic optimization algorithm to see if it's going to reach the optimum that you care about. Okay? Right, so what we're going to care about for now is minimizing a function on Rn. And so far we know that grad f is the direction of CPI's ascent. So at the very least we know that if we stand at x and we like tiptoe a little bit along the gradient, the value will increase. If we tiptoe a little bit along minus the gradient, the value decreases. So already that suggests to us like some kind of optimization algorithm, like just subtracting the gradient every time. But we don't know that that technique converges. I mean, for one, it could be that your steps get so tiny you actually make no progress. Or it could be the opposite, like how far along the gradient do you go, right? Now, these kinds of algorithms, right, they're basically justified by this fact that we essentially proved, which is that for sufficiently small alpha, oftentimes you call this the step size or the learning rate, essentially f of x minus alpha times the gradient is less than or equal to f of x. Right? If we didn't have that, we'd be in trouble. Okay. So already we have one algorithm for optimization, which is gradient descent, which just takes advantage of this property. But actually the first version of gradient descent that occurred out in nature wasn't quite the one that we're all used to. Right? So in gradient descent, what do? We have some iterate xk. And I think the version that many of you guys have coded, you compute the gradient of f, and you add a little, it's like a small multiple of the gradient to xk. But a reasonable question you might have is, well, what is that small multiple, right? Because like if there's a constant, I actually don't know. Like if I go too far along the gradient, eventually it'll start going up again. And so you can imagine if t is too big, I'm in trouble. So there's a version of gradient descent that doesn't suffer from this issue. And what it does is basically builds on what we just did previously in the lecture, which is talk about one-dimensional optimization techniques, right? And so in particular, here's a very generic version of gradient descent. I compute the gradient, and rather than just adding a constant step size, I define a new function gk of a single variable t. What do I know? I know if t is sufficiently small, then gk decreases a little bit from t equals 0, right? So one thing I could do is call my one-dimensional optimization routine, find a local minimum of gk, and then replace xk with that thing and keep moving. Does this picture make sense? So I'm kind of like taking one-dimensional slices of my function, and at least I know along that slice I can make a little bit of progress. That's what our Taylor series argument said. I'm going to find the optimal t, and then I'm going to keep going. Notice this is not the typical implementation in machine learning software, which just takes t to be a constant, but we can at least convince ourselves that in this version, f decreases in every step. Yes?
Well, we know we're decreasing in one direction, right, in every step.
Uh-huh.
How do we know that we're not going down? Well, I guess we only move in that direction.
We only move in that direction. One direction, just like the dam. Any other questions? Cool. Now, on the other hand, this algorithm feels kind of wasteful, right? Because like we're spending a bunch of time optimizing that the gradient is only the gradient at xk, right? So the second we move along gradient direction, we're no longer doing steepest descent, we're just doing descent. And so it feels like we might be able to do better than like running one-dimensional optimization all the way to convergence before we do the next step, right? And so that's the kind of trade-off we have, is we can spend a lot of time finding T star. By the way, that procedure is called line search. Okay, good vocabulary word. Or we can find a kind of crappy T star, and then we can recompute grad f and keep going. What we're going to see today, if I manage to stop talking so much, is that there's actually a really sneaky set of conditions that are like a little bit better than find a constant T star and a little bit worse than finding the best possible T star that are going to be sufficient for your algorithm to converge. Does that make sense? So like, I want to find like an okay solution to this 1D problem, but not like the best one. Does anybody have another name of these, by the way? Trivia fact. These are called the,
Approximation.
Sorry, names of what?
the name of the conditions that make sure that this kind of procedure, like a condition on T star, is guaranteed to reach a local optimum. Yeah. Wolfe conditions. That's absolutely right. Okay. And let's see why these kinds of conditions are useful. So typically in optimization, we draw level set style pictures quite a bit. So let's do that here. Let's say that I have a function. There's level sets are kind of like kidney bean shaped. This is like the worst case for optimization, at least locally, like that. Pardon me. So here, these are level sets, meaning that like as I go from one curve to the next, this is like a function of two variables. The value decreases. Like x star is like kind of there-ish. Okay, and let's say that my initial guess of gradient descent here's like xk. Now, what direction is the gradient of f? Now, one thing you might recall from calculus class is that gradients are always orthogonal to the level set of my function. So in particular, minus grad f points this way, 90 degrees, right? So this is minus grad f at xk. Now, is that really the best search direction for my problem? I mean, locally it's steepest, right? I showed that like if I put a ball here, that's the direction it would start rolling, right? But of course, if there was some way to like compute this direction, I'd be much happier. It's just, of course, I can't do that because I don't know that from evaluating f, right? So what does my line search procedure do? Well, it tries to optimize this kind of 1D slice and find a point here. But it's not obvious that I should spend a ton of computation doing that, right? Because like if I got like a little bit off, that's probably good enough to do the next iterate. Does that make sense? Notice this is a good example of where gradient descent is really ill-conditioned, right? Because if I like overstep, I'm gonna like zigzag my way into the minimum. Okay, and so essentially you can understand this picture as the kind of counterexample that shows up a lot when we talk about optimization techniques, right? So right, so as before we can check our condition for stop it. I don't know why that's in my slide. Okay, let's talk about our line search procedure. So hopefully you guys understand my point, but like one way that I could do this is find the best possible T star. In other words, minimize my function as much as possible along this slice, which is probably going to require many evaluations of f, or its gradient even if I want to do Newton's method. Or I could just try to find a point that's like kind of good enough. And that's what's going to lead us to this object called the Wolfe condition. And then our next lecture, we'll also talk about a different way to do it, which is to use a constant t, but convince ourselves that f is sufficiently bowl-shaped or whatever, that the property is good enough. Okay, so here's what Wolfe conditions are going to do. So here's the two kind of cases that we want to avoid in optimization. Let me see if I can draw a picture. Picture as follows. Essentially, there's two push-pulls that can be really a problem in these techniques. So again, I compute a search direction, like the gradient. Or by the way, in our math here, we'll just call that direction dk. So like dk could be grad f, that would be gradient descent, but it could also be like, if we were really lucky, this direction, right? Whatever, just some direction for line search. And essentially, what we want to figure out is, let's say that I propose a new step tk, right? So I solve my one-dimensional problem, and it says move like 3 inches along the gradient. And I want to know, is my gradient descent procedure globally going to converge to a local optimum? there's essentially a push-pull between two bad things that can happen. So one of them is Zeno's paradox, which is as follows. Let's say that I chose TK, for whatever reason, I was just kind of being dumb when I designed my gradient descent algorithm, to be equal 1 over 2 to the k. That kind of feels reasonable, right? Then I can certainly convince myself that t's converge. Then it could easily be the case that my steps are just not big enough, right? So I have some function like in one dimension like this. I take like kind of a big step, and then half a step, and then a half a step, and it like converges to like there. It has nothing to do with the shape of my function, and everything to do with that I chose my t's too conservatively, and I just kind of gave up. Notice this is a little bit tricky, because if I evaluate f of tk, it'll look like the values of f converge. Do you see that? Because like I just didn't go anywhere, and moreover the tk's converge, and yet I did not reach a local optimum. On the other hand, if tk is too big, I could like hop over my optimum, and then I can hop even farther and zigzag out of control. Right, so that's the kind of push-pull I need to worry about. If my steps are too big, I'll just zigzag and go crazy. If my steps are too small, I can end up in the case where I take such itty-bitty steps I never make any progress. Right, so I kind of sandwich myself between those two things. The famous result in optimization, these Wolfe conditions, let's say so long as my t's satisfy these two conditions, my optimization algorithm converges. We are not going to prove that fact. If you like this kind of thing, there's a really awesome textbook out there. It's by Nostal and Wright. I don't know who Nostal is, but Wright's a super nice guy. And essentially, they go through the proof very carefully. But what we are going to do is, at the very least, kind of illustrate what these conditions are telling us about our algorithm to give you guys a little bit of intuition. And the reason to do that is if you actually run a piece of optimization code out there in nature, what you'll see is this is the thing they check for their line search procedure. So essentially, what is going to happen in line search is you're just going to do your 1D optimization problem until you find a t that satisfies these two things, and then you'll keep rolling. Okay? By the way, another thing you should probably check is that there exists such a t, but there does. Okay, so let's quickly draw a picture of these two cases, or these two conditions to convince ourselves these are pretty reasonable things. So they look pretty ugly the way I've drawn them here. Okay? So these two conditions are I think it's Armijo rule, and then the curvature condition. And both of these basically have to do with Taylor series. Okay, so, and what they're going to do is kind of sandwich the convergence of our algorithm between two different cases here. So let's look at the first condition first. Does anybody recognize the right-hand side of this if I took C1 to equal 1? Like, it looks ugly, but let's look at it for a second. Do you see that this is the linearization of f along the search direction d? Okay. And moreover, by the way, our constant c is going to be between 0 and 1. Okay? So let's say that I have a function. These conditions are super hard to draw. Let me see if I get it right. So this is for non-convex optimization. So our function can look like that. And so this is our like 1D slice that happened during line search, right? So notice, here is the linearization of my function like that. Okay? Now C, in this particular case, you're going to choose between 0 and 1, which means you take the slope of this line and you decrease it. Okay? So I draw a second line that looks something like this guy. Okay? Now, what is the Armijo condition telling me? Well, it's saying that f of x plus tk dk, so that's like, you know, the possible next iterate for my line search condition. Well, it has to be less than or equal to this linearization. So it has to kind of sit underneath. Okay, so it's like down here. Does that make sense? Let's think about why this is a reasonable condition. Well, essentially, what this Armijo condition is called, sometimes it's also called sufficient decrease. And essentially, what it's trying to avoid is the condition where I go so far in my line search, things start to go back up. Right? Because what do I know? I know that at least in some small neighborhood of t equals 0, my function should look kind of like this slice here. So if I give it a little bit of wiggle room, it'll sit inside of that triangle. that I've drawn. But if I go too far, then now my Taylor series is a bad approximation, and I really shouldn't have been doing that, right? And so that's what this Amigo rule is saying, is it's basically trying to avoid t's that are too large. Does that make sense? Now, there's a second condition called the curvature condition. This one's even harder to draw, so get excited. and it does the following. Let's redraw this thing. And then we're done for the day, I promise. So here's my function again. I'm going to do my line search. So now I have, oh boy, function like this. Okay. And now let's take a look at what the values are on the left and the right. So let's look at dk dot grad f. Does anybody remember what this is from a few lectures ago? This is the directional derivative of f at xk. Or, to put it more simply, it's the slope of this line. Right? Because remember that the directional derivative is just the slope of these 1D slices of my function, and I'm evaluated at xk, which corresponds to t equals 0. Okay? So here's what the curvature condition does, which is kind of fun. Let's look at all the other points that have the same tangent. This actually kind of relates to Alice's question. I have to think about it a bit. So like this guy, this guy, this guy. Okay? Now, here's a kind of fun thing. What happens in between these two ones? Well, it's like a roller coaster, and it's going down really fast, faster than what's predicted, right? And then it starts to go back up, and it's a roller coaster going down again. So let's take our interval and kind of divide it like that. Essentially, what the curvature condition is saying is if I am in this region, right, so I am decreasing faster than would be predicted by my linearization, does it make sense for me to halt my optimization technique? Probably not, right? Like my ball is rolling down the hill even faster than calculus would predict, right? So the curvature condition says if I'm in that region, I gotta keep going in my line search. Which kind of makes sense, right? Because if your line search found a point here, it's a pretty good indicator you should have gone farther, right? On the other hand, in this region, now my function is going back up, right? Notice this quantity on the left-hand side of this inequality is the directional derivative at the other point, right? Well, now it's going back up, so it's not clear that line search should keep going, right? Because it's going to keep going up, yeah? So like this region is okay. This region is again not okay, and okay. Okay? So that's what these two conditions are saying. These are called the Wolfe conditions. dk is a search direction. So for example, the gradient, like the way that you're going to move along in one-dimensional line search. And the Wolfe conditions are kind of nice. They say that essentially, so long as each tk satisfies these two inequalities, which you can get just by like doing 1D optimization and just stopping when you find it. One thing that you can convince yourself is that the actual minimum of 1D, these two things are satisfied. So long as each tk satisfies these inequalities, then you won't be stuck in either of these two cases. You won't like have a Zeno's paradox, and you won't just start zigzagging out of control. Notice the zigzag one is pretty easy to check because at the very least you're making sure that like you're decreasing. Okay. And so essentially these are the conditions that people check for line search procedures. And there's a very easy algorithm that people use for line search called backtracking line search, where you just choose a giant T, check these inequalities. If they don't hold, divide it in two, and you just keep doing that. And it turns out that procedure is okay under very weak assumption. So in any event, this is sort of a nice way to do it. And what they allow you to do is to check for convergence of your algorithm. Now, something that we'll talk about in our next lecture is what if we don't want to do that? Like these line search procedures feel expensive, right? I'm solving a very big one-dimensional optimization problem in every step. One thing I could do is just be lazy and choose t to be a constant or something like that. Obviously, if t is a constant, you could end up in the zigzag situation quite easily. So think about like absolute value as the sort of canonical example. However, we can write down certain conditions on tk that might allow our technique to converge anyway. So for example, we might take our step sizes to go to 0, but then to avoid that Zeno's paradox condition, that they add up to infinity. So for example, tk is equal to 1 over k. And under certain assumptions, our algorithm will still converge. in any event, I'm going to pause my discussion here. So in our next lecture, so currently we've justified optimization procedures with backtracking line search are okay, so long as you satisfy these two conditions. Or we've at least kind of drawn a picture of why that might be okay. In our next lecture, we're going to say, what if we do the opposite? We're so lazy, we just take t to be a constant. Under what conditions can our algorithm still converge? So with that, and there's going to be our theorem. Spoiler alert. So we'll prove this thing next time. With that, everybody, please do not forget your midterm on Wednesday. If you miss it, you will get a 0 on your midterm. Cool? Cool. All right, study hard. I have office hours tomorrow, or your TAs have office hours. There's one more review session tonight, right?
Yep, 5 to 6.
5 to 6. And have a delightful first half of your week.